Hi, in this video we will be looking at the calculation of the pH of a weak base. In this example I am trying to calculate the pH of a 0.15 molar solution of pyridine, which is a weak base with the formula C5H5N. It has a Kb of 1.7 times 10 to the minus 9th. For bases, when we're looking at a base in solution, it follows the general formula of a base plus water is in equilibrium. And if we want to think about the reactants, instead of memorizing them, I always think you should go back and think about the Bronsted-Lowry definition for a base. That is a proton acceptor. So he's going to take a proton from water and he's going to become protonated, which is going to leave it with a positive charge if we start out with a positively or a neutral charged compound. And then we're going to be left with the hydroxide ion. So this is the generic relationship for any dissociation of a base solution. And the Kb stands for the equilibrium constant for base, and it's based on this below reaction. And we can write our Kb expression for that, our equilibrium expression. Again, just products over reactants. And that's going to equal the protonated base times the hydroxide concentration all over the concentration of our base. Again, we do not include water because water is a pure liquid, which does not get included in the K expressions. Now, sometimes you were given, instead of Kb in the problem statement, you may be given Ka for the conjugate acid. To go between Ka and Kb, the relationship holds that Kw equals Ka times Kb. So if we want if we are given Ka and we need to get back to Kb, we know that Kb is equal to Ka all over Kw, where Kw equals 1 times 10 to the minus 14th at 25 degrees Celsius. Sorry for the coughing. On this slide, I'm showing our major reactions that are present during this production of base. We have our water dissociation with a Kw of 1 times 10 to the minus 14th, and then we have our pyridium plus water giving us the protonated form of pyridium and hydroxide. Our major species are going to be our water and then our pyridamine. So the goal of this problem is again to solve pH. Notice that we don't have H3O plus in our equilibrium expression, so we're going to have to first solve for pOH, and then we can go back and relate that to our pH. We're going to continue to use the ICE tables to solve the problem. ICE, again, stands for initial change equilibrium. And our initial concentration here is 0.15 molar. Our H2O doesn't matter. We have no protonated conjugate acid at the beginning, and we have no hydroxide at the beginning. Our change will be minus X And our products plus x, so our equilibrium concentration will be 0.15 minus x plus x plus x. We can put this into our K expression for KB, which is going to be our C5H5H plus times our OH minus all over our pyridamine, which is going to equal to x squared all over 0.15 minus x, which equals 1.7 times 10 to the minus 9. I do think it's a good idea to always write out your reactions involved, because when you write out your KB or Ka expressions, you're less likely to get them mixed up. If you're looking at the reaction, you're always going to be able to write your products over your reactants, and you will never mix them up or flip-flop them, which a lot of people commonly do when dealing with these reactions. So here we have our KB. We're solving for x. Remember, in this case, x is going to be equivalent to the hydroxide concentration. So let's solve for this equation for x. We're going to use our small x approximation. So we're going to say that x is small, so 0.15 minus x is still about 0.15. So solving x squared over 0.15 equals 1.7 times 10 to the minus 9th. X is going to equal 1.596 times 10 to the minus 5th molar. So our hydroxide ion concentration equals 1.596 10 to the minus 5th. You can solve this two ways. I find solving POH is the easiest and fastest way to do it. So the POH is the negative log of our OH minus. And that equals 4.79. And then we have our relationship that 14 equals POH plus pH. Therefore, pH equals 14 minus POH. So 14 minus 4.79, and that gives me a pH of 9.20. Lastly, we got to check for our validate our small x assumption by calculating our percent ionization, and that is equal to our x divided by our initial base concentration times 100. And so that equals 0.01%, which is far less than 5%. So we are valid. And our answer will be correct to say 9.20. So that is solving the pH of a weak base. So you can do that anytime you are dealing with any, like an ammonia solution or any other weak base problem. Alright, keep up the good work, and I'll see you in future videos. Have a great day.